You should have chapter 8, section 2 for me, please. So when I have a relation on a set, I have this list of ordered pairs. But a giant list of ordered pairs is a pain in the neck in terms of actually representing what my relationship appears to be. There are two different versions of a representation I want to talk about in this course. There are lots of others, but I think these are the two most approachable. I'm going to start with an advertisement for next semester. I'm teaching a course called graph theory. Digraphs is a part of graph theory. So this is a sample of some of the things you will see in that course. Digraph is short for directed graph. And in this case, a graph does not mean like the graph of a function. Although a graph is a relational representation, it's not the kind of graph I'm talking about here. This type of graph is a set of vertices or nodes connected by a set of arcs. And the fact that I'm using arcs is where my directed idea comes into play. That each arc has a direction associated with it. I go from one vertex to another. So let's consider, there's a dog next door, be aware if we hear barking, that's what they're talking about. If I have a set of objects, and I'm talking about a relation on that set, I'll make a nice short set to work with. My set is just 1, 2, 3. And I'm going to find A is related to B if A is less than B. The nodes in this graph are the elements of our set. You can put them anywhere you want. I've just created dots with the numbers on them. You could have the dots with the numbers to the side. You just have some indicator of which thing is which. An arc is an arrow. I need you to draw the arrows from vertex A to vertex B if A and B are related. So a relational digraph has a rule for putting the arcs into our nodes. You're going to create In this case, how many arrows? You can write out the ordered pairs. Yes? I mean, 1 is less than 2, 1 is less than 3, and 2 is less than 3. So the things that satisfy this are the ordered pairs 1, 2, 1, 3, and 2, 3. And if we think of those as start my arrow, end my arrow, I just have to draw those arrows in. There's the ordered pair 1, 2. Here's the ordered pair 1, 3. Here's the ordered pair 2, 3. Make sense? So in this case, a directed graph, a digraph, is a set of nodes and arrows. But really, I'm still kind of working off the set of ordered pairs, yes? So even if I defined my set and then simply gave you a list of ordered pairs, you should still be able to build the digraph that goes with this relation. I have no idea what equation or rule would govern this particular relation, but I don't need that since I explicitly have the ordered pairs. Make me a picture. So you're going to end up with 9 arrows. We have 9 ordered pairs here between your sets of 4 dots. The way you arrange these 4 dots changes the way your picture looks. I'm going to go out on a limb and say I don't think any of you put your dots in a diamond, did you? Even if you had put them in a square, you might not have gone 1, 2, 3, 4. You might have gone 1, 2, 3, 4 with the 3 and the 4 reversed from where I have them. That's fine. It doesn't matter. But now I get to put the arrows in here. Two goes to 2. Goes to itself. 2 goes to 3. 3 goes to 1. 3 goes to 3. 4 goes to 1. 4 goes to 3. That, by the way, is not the original picture I drew in my notes. The original picture I drew in my notes has the dots arranged differently. Those are exactly the same picture. Sure. No, they're equivalent pictures, but they're not exactly the same. Questions? If you can, by grabbing one of these vertices or edges and stretching it or moving it or twisting it, turn one digraph into another, then you've created what are called isomorphic, iso, same, morph, form, graphs. Telling whether or not two graphs are isomorphic just from looking at the pictures is a very, very, very NP complete problem. It's hard. Question. Is this relation reflexive? I don't have the formula. How the hell am I supposed to know? I could answer this question without the picture. I could. Because I do have enough information just in the list of ordered pairs to answer that question. What does it mean for a relation to be reflexive? Excuse me. All the elements relate to themselves. All the elements relate to themselves. So in my picture, I would need to see an arc from each element to itself. A loop, like I have here or here. But I don't have a loop on 1. I don't have a loop on 4. The ordered pair 1, 1's not in my relation. The ordered pair 4, 4 is not in my relation. The answer is no. So that's my picture definition for reflexive. A relation is reflexive if in the digraph, every node has a loop, an arc from that node back to itself. I like that. I can just look at the picture. Do I see loops everywhere? No, not reflexive. If I see any one that doesn't have a loop, I'm done. Because that's a universally quantified statement. I'm going all the way back to chapter 1. Okay. Reflexive. Symmetric. What's it mean to be symmetric? The order can be flipped. Whenever I have an arc that goes from A to B, I should have an arc that goes from B back to A. Right? So now I look at our picture and I say, are there any places where you see an arc from one node to another and not an arc back? 2 to 1. 2 to 1 exists, but 1 to 2 doesn't. Same thing with 3 and 4. There's an arc from 4 to 3, but there isn't one back. And there's an arc from 2 to 3, but not one back. So there's my symmetry idea. So again, I'll write a general statement. A, B with an arrow over it. I've seen that notation before. Where have we used this notation? Not in this class. It's a vector. We used it in trig, in pre-calculus. We used it in physics. I've seen these before. From A to B. We used it in geometry as a ray, starting at point A, going through, same notation. But what I'm saying is I'm going from A to B with that little arrowhead. So I want to say if there's an arc from A to B, then there must be an arc from B to A. And again, we found 3 places where that doesn't happen. So this graph is not symmetric. Questions so far? Reflexive, symmetric, antisymmetric. Now, antisymmetric was the one that was the weird definition. I never really liked it, but I promise there's actually a good way to interpret that in this picture that is helpful. So let's go back and look at the definition of antisymmetric. What does antisymmetric say? What was our definition from Monday?
If A to B and B to A are a relation set, relation are the A to B.
So if AB and BA, then
A.
so if I've got an arrow from A to B and I get an arrow from B to A, the only way to do that is go from the node to itself. In other words, if this is my conclusion, that arrow really goes from A to A, and that arrow really goes from B to B. Wait, look at our picture here. Right here. I have an arrow that goes from 1 to 3. And I have the arrow that goes from 3 to 1. Are 3 and 1 the same thing? Therefore, this is not antisymmetric. Now, with that in mind, how can I write a general idea of what it means to be antisymmetric? I want to not have that happen. E? It's okay. Actually, I want to say it a little bit differently, but this is what we're trying to avoid, right? I'm trying to avoid an arrow from 1 to 3 and the arrow from 3 to 1 both being there. So I'm going to say you can have at most one of those two. For any 2 nodes, there can be at most, any 2 distinct nodes. There can be at most one edge between them. As a matter of fact, I'm going to phrase that even better. I'm going to say you could use an exclusive or here, couldn't you? You could have neither of them, but you can't have both of them. I like that. If you've got two different dots, they can have at most one arrow. They might have no arrows between them. You'll notice there are no arrows between 2 and 4. That's perfectly fine. I don't have to have an arrow from 2 to 4. But if I want anti-symmetry, I only have one of the two possibilities, from 2 to 4 or from 4 to 2. Can't have them both. What's left? Oh boy. Problem. Transitive is hard. What's the definition for transitive again?
A and B, and B and C, and A and C.
So if I have A and B, and I have B and C, then I have to have A and C. Maybe? So how do I figure this out? Okay, here's the problem. I have to look at all possible collections of 3 nodes. In order. That gives me 64 possible options here. 4 times 4 times 4, right? So I would say, okay, I'm going to go from 1 to 1, 1 to 1. Can I go from 1 to 1? Well, I don't have a 1 to 1, so I don't have to worry about that, right? That takes out the first option. I can go from 1 to 2. No, I can't. That takes out the second option. 1 to 3. I can go from 1 to 3. I can go from 3 to... No, I can't go from 3 to 2. The only other place I can go from 3 is 3. So if I can go from 1 to 3, 3 to 3, can I go from 1 to 3? I think of this as a triangle. From 1 to 3, from 3 to 3. Can I go from 1 to 3? I literally draw this picture for each setup. If I want to go from A to B and from B to C, I have to have A to C. So now I have to start looking at all the possible triangles in this picture and hoping that I can get there in the correct orientation. I actually think that this fails. But in order for it to fail, I need to find a counterexample. I need to find one set of 3 where this fails. Colin?
2 to 1, 1 to 4.
2 to 1, 1 to 4. But I can't cut across. I can go from 1 to 4, 4 to 3, but I can go from 1 to 3. I can go from 2 to 3, 2 to 1, but I can go from... So that's our exception right there. 2 to 1, 1 to 4, but not 2 to 4. Oriented triangles is the way I want to think about this. But I'm the first person to tell you that's hard. That's a non-trivial examination of a lot of different options. Especially, I only had 4 here. And if I really wanted to brute force this, I'd be looking at 64 different options. Now imagine a graph with I don't know, 15 nodes. Hell, 12 nodes. 12 cubed is 1,728. Mother. 15 cubed is 3,750. I'm going to be here a long time, man. I don't want to do this. That's wrong. 225 times 15. It's 22, 15, 11, 25. It's 3125. Sorry, wrong number. Still, it's a crap ton of triangles I don't want to deal with. If I have a very few number of edges, if the number of edges is sparse, there's some technical definition of what makes a sparse graph. Count the number of edges that are there versus the number of edges that aren't there. I'm not going to worry about that. It's easier when I have very few edges because there are very few possible triangles from the look at. When I have a lot of edges, I'm in trouble. So as much as I like a digraph, it's not as helpful as it could be, especially when it comes to transitive. On the other hand, reflexive and symmetric, those are really easy off this picture. I have to look for arrows that are alone to violate symmetry. I have to look for loops to violate reflexiveness. If I'm missing a loop, I'm out. If I'm missing a back, I'm out. So what else can I do? I need another method of representing a relation. Digraphs only work on a relation on a set. We have to be going from that set to itself. Otherwise, my edges have to go to things that aren't there. That's a bad idea. So let's generalize this idea. I'll come back to this example in a minute. And let's instead create a relational matrix. I am terribly sorry to tell you that there is no bullet time event for this particular piece of entering the matrix. I have a from and a to on the arcs, but in general, relation goes from one set to another. So if I think of a relation going from set A to set B, I'm going to be very specific here. I am going to have a certain number of elements in A and a certain number of elements in B. Now, frequently I would use, for a matrix, I use M and N for the numbers that I have just replaced by R and C. R and C. I said something about this on Monday. When I first talked about a relation, I gave you a couple of visuals, right? The first visual I gave you had the elements of A in one column and the elements of B in another column. I drew arrows. I basically made a relational graph, but it wasn't from the set to itself, so it really wasn't the digraph. Then I made a chart. And the chart had elements of A in rows and elements of B in columns. So now I'm creating an array. And this array will have R rows, one row for each element of A. And it'll have C columns, one column for each element of B. And then I'm going to call this matrix M. Normally, when it's a matrix for a particular relation, we might call it M of R. Sometimes we'll call it M in square brackets with an R underneath it. Sometimes we'll just call it square bracket R because it's the matrix for a relation. Those square brackets are the things that hold my matrix together. So I have all of these entries. All a matrix is it's a big two-dimensional array. And I can think of indices. I've got row 1, row 2, row 3, all the way up to row R. I've got column 1, column 2, column 3, all the way up to column C. That, by the way, means that one is column C minus 1. I'm going to pick any dot somewhere in the middle here, and I'm going to call that dot Mij. That's the thing in row I and column J. Excuse me. So here's the deal. Each of those M's, little Mij, is either a 1 or a 0. So this is a matrix with binary entries. It's a 1 if AI Bj is in my relation. And it's a 0 if it isn't. That's it. I put a 1 where things are in the relation. I put a 0 where they aren't. This idea applies to any relation, whether that relation is on the set, so from A to A, or from one set to another. Example. I want to create a matrix for this relation. From the set 1, 2, 3, 4 to the set 1, 2, 3. Relation is defined A is related to B if A is strictly bigger than B. So I'm going to have a matrix that's got 4 rows and 3 columns. Again, row, column, Roman Catholic institution, RC cola, take whatever memory you want. RC, we're going to call this a 4 by 3 matrix, 4 rows by 3 columns. If it helps, outside the matrix, put the elements of A going down the left column or the right column. If it helps, put the elements of B going across the top or across the bottom. You are welcome to add these sorts of annotations outside your matrix. So you've got 12 spots. Each spot gets a 1 or a 0. Let's go across the top row. 1 or 0. Because 1 is not less than 1. I want A bigger than B. That's not true here because this is the A side and this is the B side. What about here? Here. There we go. Whole first row is zeros. Second row. Ta-da. This is our matrix for this relation. I like it. If my relation is on a set, then something nice happens to the size of my matrix. If I'm going from the set A to the set A, how many rows, how many columns? Wait. 4 and 4. For this example, but in general, it's however many things are in A, right? Which up here was the number we called little r. But I can just say it's the same size. We call such a matrix a square matrix. So let me go back to the example we did earlier. Here comes our picture and our relation from our digraph, right? We could do either of these. Let's do the complicated one. I'm going to get a 4 by 4 matrix. 4 rows, 4 columns. But because I already have all of the ordered pairs listed out, I even cheated in the way I listed out these ordered pairs. You'll notice that the ordered pairs are in order. The first number goes from smallest to largest. And then the second number goes from smaller to larger within each of those, right? If these were letters, they'd be in alphabetical order. But I don't have that same idea for numbers. So we call it lexiconographical. I love that word. It just means in the order in which the word would be written. 1-3 is smaller than 1-4. 1-4 is smaller than 2-1, which means this is the top row. That's row 1. Because row 1 is going to have all the things that have a 1 in the first column, first entry, right? It's A and B. So 1-1, nope. 1-2, nope. 1-3, yes. 1-4, yes. And I can just go across this list. 2-1, yes. 2-2, yes. 2-3, yes. 2-4, nope. And I just yes, no my way across the list. 3, 1, 3, 3, 4, 1, 4, 3, not 4, 2, not 4, 4. You with me so far? I just took everything away. No picture, no list. From here, is this relation reflexive? I know the answer to that question because we already came up with the answer to that question. We already did this from the digraph. But how from here can I tell if this is reflexive? Because that's 1, 1 and 2, 2 and 3, 3 and 4, 4, right? I'm even going to name that stretch. I'm going to call those the entries on the main diagonal. Remember how we called them MIJ? Well, these are the things that are MII. 1, 1, 2, 2, 3, 3, 4, 4. R is reflexive if and only if MII is 1 for all I. I like that. I just have to look for ones, just like I had to look for loops. This is easy. So let's ask the other three. Symmetry. How would I know from this matrix whether or not my relation is symmetric? I can spell too. Almost. It's not just these numbers. It's everything that's not on the diagonal. So let's ignore those 4 numbers and just look at the others. I can't quite make it. I wrote this badly. I want to be able to see that 1 down there, and I really can't. I want those sets of numbers, the numbers in that upper triangle and the numbers in that lower triangle, to match. I want to fold this across the diagonal and have the numbers be in the same spot. If I have 2, 1, I'm going to need 1, 2. If I have 1, 3, I'm going to need 3, 1. So if I ever see a pair that doesn't match, I can stop. It is symmetric if and only if Mij is equal to Mji for I and j different numbers. Technically, any matrix that satisfies this property that is square is called a symmetric matrix. Gee, I wonder why. Because if I fold it over, it's the same thing. That is exactly the same definition I'm going to use for symmetry in a relation. If the matrix is symmetric, then the relation is symmetric. By the way, this makes antisymmetry work on the same idea. Because antisymmetry says, I'm going to compare those, and I'm going to compare those, and I'm going to compare those, and those, and those, and those, and those, and what do I need to happen? Almost. They don't have to be different.
They don't always do.
No, that would just make it not symmetric, right?
Or they can just both be zero.
Right. If I add, I can't get anything bigger than a 1. I can never have a 1, 1. I could have a 0, 0. I could have a 0, 1. I could have a 1, 0. But I can't have 2. Transitive. Okay. Transitive actually requires me to do formal logic with ands and ors. I have to think about binary formal logic. If I think about the truth table, remember this? Chapter 1 was a long time ago, man. I don't want you to use T's and F's. I want you to use 1s and 0s. I mean, this was like January, man. If I'm doing and, it goes like that. If I'm doing or, it goes like this. George Boole, who came up with the idea of Boolean algebra, which is arithmetic on logic, said, what I want to do is think of this like multiplying. What's 1 times 1? What happens when you multiply by 0? So all 3 of those should be 0. Now, that's multiplying. The other one adds. But you can never get a number that's bigger than 1. So when you add 1 and 1, you get 1. But when you add 1 and 0, you get 1. When you add 0 and 1, you get 1. When you add 0 and 0, you get 0. So this is multiplying and adding. Okay. Remember I said these were sets? We could do set operations. I can OR my 2 matrices, and union is the symbol for OR, isn't it? I can do an AND by doing the AND of the 2 matrices. Here's the best part. How many of you have done vectors in any other class anywhere? You remember a thing called a dot product? When you take the dot product of 2 vectors, you take the first numbers and you multiply them. You take the second numbers and you multiply them. You take the third numbers and you multiply them. You take the last numbers and you multiply them. And then you add all of those up. With me so far? Replace multiplying by and. Replace adding by or. This is called a Boolean product. If I have two matrices, I can multiply them together by going across each row and down each column. So if I have a 4 by 4 matrix, I'm going to do the first row times the first and the second and the third and the fourth. Second row times the first and the second, third, and the fourth column. It's always the row on the left and the column on the right. That's why I wrote it in this order. It's row column, RC again. If you take this matrix and multiply it by itself, then you've gotten the matrix for R composed with R. Which would be the matrix times itself, wouldn't it? Matrices give me a shortcut to transitivity. That's the way I can tell if it's transitive. I don't have to look at triangles. I have to do the matrix arithmetic. I like transitive relations. I like symmetric relations. I like knowing all of these things about my relations. There are certain relations that have all the nice characteristics I want, and we've been using them almost all semester. I'm going to talk about those on Friday. I will see you all then. Have a wonderful rest of your day.